So this is a nice, easy, well, at least easy for Olympiad standards, question from the 2009 Irish Maths Olympiad. It's just you try it by yourself. You can do it with just leaving cert maths and then come back to see my solution when you either have tried it, done it yourself, or not, and you just want to see how I did it. So the first thing I did is I just follow exactly what this says. So p of x be a polynomial with rational coefficients. Okay, so we can say p of x is equal to, so I'm just going to call the coefficients a0 and then a1x plus a2x squared. So all these a's are just random rational numbers that are the coefficients of the terms in the polynomials. Plus, and then eventually we'll have a sub, and I'm just going to say it goes up to k. So it goes up to k minus 1, and then finally it goes all the way up to k. I'm not going to use n just because there's an n here. I don't want to cause confusion. Now we also need to know what p of x plus n is. Now before I do that, I'll just state very clearly that a0, a1, and a2 ... they're all elements of the rational numbers. So that's q. Now we'll need to get p of x plus n as well, which is equal to a0 plus a1, and instead of x, we'll have x plus n, plus a2 times x plus n, the whole thing squared, plus ... plus all the way up to a sub k minus 1 times x plus n to the power of k minus 1, plus a sub k times x plus n to the power of k. Right, and now to get q of x, we just need to subtract these from each other. So for q of x, we'll just have this big thing minus this big thing. Okay, and we'll see that something very nice happens here after a little bit of messing around. So you can see that the a0s will cancel, and we will get, basically, we're going to get, that'll cancel, and we'll get a1x plus n times x plus n minus a1x plus a2x plus n squared minus a2x squared plus ... that keeps happening, plus a sub k minus 1, oops, that minus 1 should be up there, times x plus n to the power of k minus 1 minus a sub k minus 1 x to the power of k minus 1. And then finally plus this, and then we'll have minus the other bit at the bottom. Now we'll see that some nice cancellations will happen. So as you can see over here, for example, this x, a1x, will cancel with this a1x. The same will happen here if we were to do the binomial expansion, which I will show now, just to demonstrate. So if we factor out a1 from these, we get a1, so that's equal to this. It's equal to a1 times x plus n minus, and then this x, plus a2, and then if we expand out this bracket, we'll get x squared plus 2nx plus n squared, and then factor out the a2 as well, and we get another minus x squared. X squared and this x squared will cancel, so they're gone. So is this plus, because you don't need it. And then these x's are gone too, and we can just clean things up a little bit. Alright, and this is going to keep happening for all of them, but we'll just show how it happens for the k minus 1th term. So when we factor out a sub k minus 1, well, when we expand out this binomial, we're going to get, now you can write the choose function, but it's not necessary because obviously the coefficients don't matter, it's just what we're doing with them, okay? So when we expand out this big bracket, we're going to get x to the power of k minus 1, then we're going to get some number times, which I'm just going to call k1, just for simplicity, or I'll call it k, no, not k is confusing because we already use k, I'll call it b. B sub k minus 2, and then we'll have x to the power of k minus 2 times n, and then we'll have b sub k minus 3 times x to the power of k minus 3 n squared. So this is just a binomial expansion, except instead of writing the coefficients as like k minus 1, choose 1, just to save time, I'm just writing them as b, just because the numbers don't actually matter, and this will just keep going on, plus ... and just the rest of that expansion, then we'll have n to the power of k minus 1 as our final term. Then we have minus, and then this x to the power of k minus 1. So we'll have minus x to the power of k minus 1. And you can see that'll cancel with the first term, giving us just the rest of these terms. And the exact same thing will happen with this last term, which I'll do out quickly. So we'll have plus a sub k, factor that out. Then we'll have x to the power of k. Then we'll have plus, now I used b here, I'm just going to use c as my coefficient. So we'll have c sub k minus 1. Then we'll have x to the power of k minus 1 times n. Then we'll have plus c sub k minus 2. Then we'll have x to the power of k minus 2 times n squared. Plus that'll keep going on. And then the last term will be plus n to the power of k, as per the binomial expansion. Then we have minus and then x to the power of k. Now these x to the k and x to the k cancel, and we're just left with this. Now one thing we can notice is that every single term here has an n. This has an n, both of these have an n, both of these have an n, because the terms with only the x, they all ended up cancelling. So we can actually factor out an n from everything here. So we'll have n multiplied by, then we'll have a1 plus a2 times 2x plus n plus dot 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 plus a sub k minus 1 times n. Or sorry, not times n, I already factored out the n here. That'll be times the, for example, the coefficient b sub k minus 2, x to the power of k minus 2. But then since we factored out, since we factored out this n, it's not going to be here because it's out here. Then we'll have b sub k minus 3, x to the power of k minus 3, n instead of n squared because we factored it out, plus dot dot dot. And that goes up to n to the power of k minus 2 because we factored out an n. Exact same story with this a sub k here. So we're going to have the exact same thing, except because we factored out an n, this n is going to be gone. This n is going to become go from n squared to being just an n. And this is going to go from being n to the power of k to n to the power of k minus 1 because we took out one of the n's. Okay. Now, okay, so there's a few things we need to notice here. A1, A2, AK minus 1, all of these A's, as we stated up here, they're all rational. So that's important. And then all of these B, the coefficients of a binomial expansion, they're always also going to be, they're always going to be an integer, or even more specific, they're always going to be a natural number, because that's just how the choose function works in Pascal's triangle and stuff. That's not really the topic of this video, and same here. So we have n times all these a's. It's only the a's that we have to worry about. As I said, the binomial coefficients, they are always whole numbers anyway. We just have to worry about these a's. So just to make this a bit more clear, I'm going to write each a. So I'm going to write each a for, let's say, ak. I'm going to write this as, I'm going to use Greek letters just to avoid confusion with mixing up with the letters we've already used. I'll call it alpha k over beta k, where alpha k and beta k, they're both just going to be some integers. So since ak is rational, it can be shown as a ratio of two random integers. So just to make the problem a bit more clear, I'm going to rewrite this using those. So we'll have equals n. Now instead of a1, I'm going to write alpha 1 over beta 1 plus alpha 2 over beta 2. So these are still rational numbers. I'm just writing them as fractions to kind of show what I'm going to do a bit more clearly. And then we'll have, instead of a sub k minus 1, I'm going to write alpha sub k minus 1 over beta sub k minus 1 times, and then we'll just have this big bracket, which I'm too lazy to write out again. I also forgot to write in a plus here, it seems. And then we'll have, instead of ak, I'm going to write plus alpha k over beta k. And then this is going to stay the same. Now, you can see, the question was, we need to choose an integer n such that this polynomial has integer coefficients. Well, what n could we choose? We'll prove that you can always choose an integer n. Well, we can always choose an integer n here to give us integer coefficients here, because this is our polynomial here. This is q of x, this big part here. Well, this isn't q of x. This is q of x with an n factored out, technically. So, but this whole thing here is q of x. And the only fractions we have are these betas in the denominator. So what we can actually do is, if we let n be equal to beta 1, beta 2, beta 3, dot, 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 beta k minus 1, beta k. You can see then if we let n be equal to that and we multiply that into our big bracket, so instead of n, I'm going to write this big beta thing, or I'm letting n be equal to these betas. And remember, beta, all these betas, they're all integers, as I said here, because ak is a rational number, so alpha k is an integer and beta k is an integer. So all of these are integers, which means n is an integer, so we've chosen an integer n. And when we multiply this n into the rest of the brackets, you can see b1 will cancel with this b1, this, sorry, not b, beta, this beta 2 will cancel with this beta 2, this beta 3 will cancel with this beta, well, if there is a beta 3, the beta k minus 1 will cancel with this, and the beta k will cancel with this. So we end up cancelling out all of the fractions, which means this whole thing here only has integer coefficients, and these are all integers. Therefore, you could say the beta k's will cancel with the stuff in the square bracket. Therefore, all the coefficients will be integers, since both alpha k and, well, all of the alphas, since I'll say alpha 1, alpha 2, ... up to alpha k, and beta 1, beta 2, ... up to beta k are also integers, are an element of the integers. And that's, I think that'll be formal enough for a final conclusion. So basically, integers, these fractions will be gone, and these are all just integers anyway. N is an integer as well, and therefore we have a solution. We can always choose some positive integer n, such that this will have integer coefficients. And I guess probably should have stated that n will be positive as well, because it doesn't matter whether these coefficients are positive or negative, I don't think, because we just wanted to have integer coefficients, so it doesn't matter whether this is positive or negative, because either way, it's going to get rid of the fraction. That's the main thing. The sign doesn't matter. All that matters is that we get rid of the fraction, then all the coefficients are integers, and therefore we are done.